Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning in to this video in which we'll go through everything you need to know for your upcoming test. So we'll go through parabolas, which is the main topic, and also go through circles and then exponentials. So we start with parabolas. So a parabola is the graph of a quadratic equation, and the simplest quadratic equation is just y equals x squared. It needs that x squared term to be a quadratic equation. So I'm going to graph that using a table of values. So note, we don't normally want to use a table of values to graph a parabola because it won't always tell us the important features, but I'm doing this just to start off. So let's graph y equals x squared. So what I do with a table of values is I picked all of these x values, I substitute them into this equation to find the corresponding y value. So if x equals minus 3, y equals minus 3 squared, which is positive 9. So make sure when you substitute a negative, you always put it in brackets in your calculator. So you need to put it in your calculator like this to get the right answer. So if x equals minus 2, y equals minus 2 squared, which is 4, and so on for all of these points here. So each column is a point, this is a point, this is a point, this is a point, and so on. I'm going to plot all of these 7 points, one after the other, and join them up. So I'll start with minus 3, x is minus 3 is here, minus 3, 9 is up here. Then I have minus 2, 4, minus 1, 1, 0, 0, and I do so for the other 3 points as well. So now I've plotted all the points, I'm just going to join them up. So all parabolas have this kind of bowl shape. So they're either going to be this shape, like a smiley face, or a frowny face. Of course, this one more resembles a smiley face. So what else you might know is that this is symmetrical. It's symmetrical about this line. All parabolas have one of these called an axis of symmetry. So the axis of symmetry is always a vertical line that goes through what we call the turning point. So the turning point here is this one, because what's happening with the graph is it's coming this way, going down, it sort of stops and turns around. So that's why we call this the turning point. So for this green parabola, the turning point is 0, 0. The axis of symmetry, because it's a vertical line, it has an equation x equals a number. In this case, it's x equals 0. The x-coordinate is 0 all along this line here. The parabola is symmetrical about that line. So this parabola also has a y-intercept. In fact, all parabolas have a y-intercept. The y-intercept turns out also to be 0, 0. So in this particular case, the y-intercept was the same as the turning point, but that's not always the case. You'll often see parabolas have a different turning point to their y-intercept. This parabola also has an x-intercept, which is also 0, 0. So once again, not all parabolas will have the same point as their x-intercept and y-intercept. It just happens for this particular case here that the x-intercept, y-intercept, and turning point are all the same. So note, not all parabolas have x-intercepts. They will always have a turning point and an axis of symmetry that goes through the turning point. They will always have a y-intercept. They will always have 0, 1, or 2 x-intercepts. So they may not have an x-intercept. So those features are very important because they're actually how we're going to graph other parabolas. As I said, we don't always want to use a table of values because it won't always tell us what these important features are. Knowing the graph of y equals x squared allows us to graph other parabolas. So if we have a quadratic equation in this form, it's called turning point form. So that's where we have something times x plus or minus something squared plus something. It's got the brackets and the square. That's what makes it turning point form. We call it turning point form because you can easily read off the turning point. If it's in this form, this first value tells you the x-coordinate of the turning point, but it's the negative of that. The negative of that is the x-coordinate of the turning point, and then this value here by itself, outside the brackets, that's the y value of the turning point. So let's graph one that's in this form. So let's graph y equals x minus 2 all squared plus 1. That's in turning point form because we have x plus or minus something squared and then a number by itself. So this value here, you take the negative of it, and that's the x coordinate of the turning point. And then the other value by itself is the y value of the turning point. So this parabola, this equation written in yellow, its turning point would be 2, 1. So I'll go and plot this point in yellow, 2, 1, which is here. This is not enough to know what the parabola is going to be. We don't know whether it's going to look like that or it could like that. We don't know. We need a bit more information. So I'm now going to find the y-intercept. So to do that, all I do is let x equal 0. So if x equals 0, I would have y equals x minus 2 squared plus 1. So if I put that straight on my calculator, I get 5. The y-intercept is 5. So let's mark the y-intercept here at 5. So again, that's still not enough to know what the parabola will look like. I still don't even know whether it's a smiley face or a frowny face. Now that's totally determined by this here, this number in front. It'll turn out to be the coefficient of x squared. So it turns out if A is positive, smiley face, and if A is negative, it will be a frowny face. So that helps me know what this parabola is going to look like. I still only have 2 points though, so whenever you want to graph a parabola, make sure you know at least 3 points. You can use turning points, x-intercepts, y-intercepts, some combination of them or whatever, but we need at least 3 points. Now it turns out this will not have any x-intercepts because it's been shifted up above the axis. I know this is going to be the turning point. It's going to be the lowest point. So there's going to be no x-intercepts. So when you only have 2 points, we need to find another. I can substitute any value I want for x, find the corresponding y value. So let's substitute x is 1. So then y would be 1 minus 2 squared, which is negative 1 squared plus 1, which gives us 2. So it also goes through this point here. Now, because this is the turning point 2, 1, I know that it's going to be symmetrical about this line here, x equals 2. So it's also going to go through that point. I didn't need a 4th point, it just helps me. So now I know that the graph is going to look like this. So this yellow graph is the same as y equals x squared, but it's been shifted 2 to the right and it's been shifted 1 up. So it's just the parabola being transformed. Okay, now we're going to graph parabolas where the equation is not in turning point form. Please pause and copy this down if you need. So let's look at these 2 equations on your screen, the red and the blue equation. Neither is in turning point form because we don't have x plus or minus a number in brackets all squared. We can't actually easily read the turning point from these 2 equations. Now note, if we wanted to put this in turning point form, in the previous form, it would take quite a lot of work. We'd actually have to use completing the square, which is complicated. So instead, we're going to come up with another method. This method will involve finding 4 features of the parabola, plotting them, and joining them up. So note, if you get an equation in turning point form, you can easily convert to this form, which is y equals something times x squared plus something times x plus something. It's easy to go from turning point into this, but it's not easy to go from this into turning point form. 4 features that we're going to calculate. We're going to calculate first, is the parabola going to be a smiley face or a frowny face? So it's a smiley face if A, the coefficient of x squared is positive, and it's a frowny face if the coefficient of x squared is negative. So secondly, we're going to calculate the y-intercept. So that's actually just C. That's just the value of the constant term by itself. Because if we say in the first one, let x equals 0, this bit here will just be 0, and you're just left with 12. So the number by itself, C, is the y-intercept. So to find the x-intercepts, what you need to do is let y equal 0 and solve the quadratic equation. As I said, there will be 0, 1, or 2 x-intercepts. And the last thing we're going to calculate, we can calculate the turning point and the axis of symmetry in one. So the x-coordinate of the turning point is x equals minus b over 2a. This is also the equation of the axis of symmetry. And then what you do is you sub into the original equation, sub in this value for x to find the y value of the turning point. When we've got these four features, we plot and graph them. So let's look at the equation in red. So firstly, the coefficient of x squared is 1. It's positive, so this will be a smiley face. Secondly, as we discussed before, the constant term is 12. If x equals 0, y equals 12. So 0, 12 is the y-intercept. So to find the x-intercept, I take my equation and let y equal 0. So I've got 0 equals x squared plus 8x plus 12. So you can either use the quadratic formula or factorization to solve this. I'll use factorization. Two numbers that multiply to 12 and add to 8 are 6 and 2. So the two solutions to this are x equals minus 6 and minus 2. This has two x-intercepts, one at minus 6, one at minus 2. So to find the turning point, I let x equal minus b. So that's minus b is 8 over 2 times a is 1, which is minus 4. That is the axis of symmetry. That is also the x-coordinate of the turning point. To find the y value of the turning point, I simply substitute this in to the original equation. So it will be x squared, substituting a negative, I need brackets, plus 8 times x plus 12. And putting that in my calculator, I get minus 4. So the turning point is actually x equals minus 4, y equals minus 4. So I'm going to go ahead and plot all these on my axis. Now it's important that I label my axis. So I know the x-intercept is at minus 6. This is only minus 6 if I label it. So I've got to go through and label my axes. Of course, negatives on the left-hand side and positives on the right-hand side. I also need to make sure I label the y-axis. So here, the y-intercept was 12. So you can see I don't have 12 divisions going up this way. So there's no reason I have to go up by 1. I could just go up in 2s. So I can mark this as 2, 4, 6, 8, 10, 12. And that means, of course, on the bottom I'd have minus 2, minus 4, and so on like that. Make sure your scale is consistent. Okay, now I'm going to plot all of these features. So I can't really plot the orientation, but I will use it. So the y-intercept of the red equation was 12, so I plot that there. The two x-intercepts are minus 6 and minus 2. The turning point is minus 4, minus 4. I know that because it's a smiley face, it's going to go this way. It's going to come through the x-intercept, stop at the turning point, turn around, go through the other x-intercept, and then up through the y-intercept. Now I need to put arrows on this because it goes on forever. So I've now graphed the red parabola. Let's look at the blue one. So I'm going to get rid of my red working out. Please pause and copy down if you need. Okay, let's look at the equation in blue. So here the coefficient of x squared is actually negative 1. So because a is negative, this is actually going to be a frowny face. So secondly, the y-intercept is the constant term, it's just minus 4. So to find the x-intercepts, once again, I let y equal 0. Now note, this is non-monic because the coefficient of a is not positive 1, it's negative 1. So I can't just find two numbers that multiply to negative 4 and add to negative 4 because it's not monic. So in this case, I'm actually going to use the quadratic formula. So I calculate the discriminant, it's b squared minus 4 times a times c, which actually gives me 0. So using the quadratic formula, I have x equals minus b plus or minus the square root of discriminant over 2 times a, in this case, is minus 1. So I actually get minus 2 is the x-intercept. So this one has only one x-intercept. It turns out that when you have only one x-intercept, that will also be the turning point. But let's use our formula here to just double check that. So x-coordinate of the turning point would be minus b over 2 times a, which gives me minus 2. And if I substitute that into my original equation, I get x is minus, I have to put it in my calculator like this. Minus x squared minus 4x minus 4. Putting it in my calculator, I do in fact get x is 0. So what does that mean? Well, I have that the y-intercept is minus 4, so I mark that there. The x-intercept is minus 2. It's also going to be the turning point. Now, I know that this is a frowny face, so it's going to go like this rather than go like that. So as I said before, if you've only got 2 points like I have here, I need to find a third one. So I know that this is going to be the axis of symmetry, so I can use that. I know that because it's symmetrical about there, it's going to go through this point here, because this point is like symmetrical to the y-intercept there. So now I've got the 3 points. I've got the turning point, the x-intercept, the y-intercept. I know its orientation. I know what it's going to look like. It's just going to go through this point, stop at the turning point, which is also the x-intercept in this case, turn around and go like that. So there we are, done. The last thing we should do is just label each parabola with its equation. Okay, now we're going to go through applications of parabolas. Please pause and copy this down if you need. So let's look at this question here. An object thrown from the ground, its trajectory is given by this equation here, y equals 5x minus 0.5x squared. Y is the height in meters, x the number of seconds after the object is thrown. We're going to graph the trajectory and calculate all of these things here. So let's start by graphing the trajectory. The equation that we want to graph is y equals 5x minus 0.5x squared. So just so we're clear, in this case, a, the number in front of x squared is minus 0.5. B, the coefficient of x is 5. Now there's no c written, so we assume it's 0. So the things that we did in the previous slide, we can do here. Firstly, because the coefficient of x squared, because a is negative, it's going to be a frowny face. Secondly, the y-intercept is the constant term, but there is no constant term, so the y-intercept is going to be 0, 0. So let's now find the x-intercept. So if I let y equal 0, I get this. Okay, so you can choose to factorize or use the quadratic equation. In either case, you should get x equals 0 and x equals 10. They are the two x-intercepts. So to find the turning point, it's going to be minus b over 2 times a, which in this case is minus 5 over minus 1, which is positive 5. So if x is 5, y will be 5 times x minus 0.5 times x squared, which is 12.5. So the turning point will be 5, 12.5. Let's plot all of these features. So we have the intercept at 0, 0, and we have the other intercept at 10, 0. Plotted the y-intercept and the two x-intercepts. We now plot the turning point. So it's x equals 5, y equals 12.5. So once again, it's important that we label our axis. You don't need to label every division, but you have to label some of it so we know that this is going up by 1 each time. So 5, 12.5 is up around here. So we know that it's a frowny face. It's going to go this way, stop at the turning point, turn around, and then come down and hit the x-axis again. Now, we only are graphing the first quadrant here because y is distance and x is time, and we can't have negative values for either of those. After graphing this, these questions here become really, really easy. So the initial height of the object is the y value when x is 0, because x equals 0 means 0 time, initial height. So the initial height of the object was 0 meters above ground level, so that means it was at ground level. That's where it started from. So the maximum height that the ball reaches? Well, that's just the maximum y value, which comes from the turning point. So it's this y value of this point, which we found was 12.5 meters. So the time it takes to hit the ground, so that's when ground level is 0, and we can see that it returns to the ground after 10 seconds. So that's all there is. So the graph has made this much, much easier. So we're now going to do another question involving applications of parabolas, but this one we won't actually draw the parabola. So please pause and copy this down if you need. Let's do this question here. The perimeter of a rectangle is 88 centimeters. What's the maximum possible area it could have? So I know this involves parabolas because it says maximum area. So remember, if a parabola is a smiley face, it has a minimum turning point, a minimum y value, and if it's a frowny face, it has a maximum turning point or a maximum y value. So parabolas are good for maximum or minimum problems. So we're going to let x be something first. So to find the area, I can't get that straight from the perimeter. I need to find the dimensions of the rectangle. So I'm going to let x be the length of this rectangle. So if the perimeter of a rectangle is 88, the two dimensions, the length and the width, add to half that. They add to 44 centimeters. So the width will be 44 minus whatever the length is, 44 minus x. So that means the area, I'm going to let y be the area of this rectangle. It will be length times width. So now we have a quadratic equation. Of course, if I expand this, I get y equals 44x minus x squared. All I need to do is find the maximum possible y value. I don't even need to graph this. If I did graph it, I know it would be a frowny face because the coefficient of x squared is negative. And I know that it would have a maximum y value or a maximum turning point. But we already know how to find the maximum turning point, how to find the turning point of a parabola without graphing it. And the turning point occurs at x equals minus b over 2a. So here b is 44, so we've got minus b over 2 times a is negative 1. So here we get x equals 22. The maximum area occurs when x is 22. The length is 22, but it means the width is also 22, 44 minus 22. So therefore, the maximum area is just going to be area equals 22 times 44 minus 22, 22 times 22, which is 484 centimeters squared. That's the maximum possible area. So yes, this shape would be a square because the length and width would be the same, but a square is a type of rectangle. So there we're done. The maximum possible area is found. Now we're just going to look quickly at finding the equation of a parabola given its graph. We're going to find the turning point of each of these parabolas. Sorry, they're poorly drawn. So let's start with the red one. So we can't find the equation of either without knowing the scale. This highlights why it's so important to label your axis. We don't know what the turning point here is unless it's labeled. So actually it's going up by 1 each time, but that has to actually be labeled. So we can see the turning point of this parabola is 3, 5. So if you know the turning point, I can find the equation pretty easily because of what I said before about turning point form. So the turning point of the red parabola being 3, 5, remember, that means the equation will be in the form a x minus the x coordinate of the turning point squared plus the y coordinate. So this is what the equation is going to look like. I just need to find what a is. So to find a, I'm going to substitute in another point. So this point will be a good one. This is the point 0 minus 5. So to find what a is, I'm going to substitute x equals 0, y equals minus 5. Because I don't know what a is. It could be 1, 2, 3, whatever. Hopefully you realize a has to be negative because the parabola is a frowny face. So substituting this in to this equation here, I get y equals a times x minus 3 squared plus 5. So minus 3 squared is positive 9, so it's a times positive 9 plus 5. So subtracting 5 from both sides gives me negative 10 equals 9a. Divide each side by 9. This is just a linear equation. I get minus 10 over 9 equals a. The equation is y equals a, which is minus 10 over 9, a little less than negative 1, x minus 3 squared plus 5. How easy is that? So let's look at the blue one. So the blue one's different because I don't quite know what its turning point is. So I can't find this here. Can't use this method. But what I do know is that this will be in the form of something times x plus 4, x plus 1. Why is that? Because the x-intercepts were minus 4 and minus 1. So if x is minus 4, it'll make this bracket equal 0. It'll make y equal 0. And if x is negative 1, it'll make that bracket equal 0, and thus y equals 0. So if you know the two x-intercepts of a parabola, the equation will be in the form y equals a times x minus the first intercept times x minus the second intercept. So once again, I want to find what a is. So I have another point marked up here because this is going up by 1. The y-intercept is 8. So I'm going to sub in, again, the y-intercept, x equals 0, y equals 8. So I get y equals a times x, which is 0, times x plus 1. So now I have 8 equals a times 4 times 1. 8 equals 4a, a equals 2. So the equation in blue is y equals 2, x plus 4, x plus 1. And we could easily expand this. You'd get y equals 2x squared plus 10x plus 8. And we are done. So that's all I wanted to go through with parabolas. I'll now go over to circles. Again, please pause and copy this down if you need. So the graphs of circles are actually really easy. If you have an equation x squared plus y squared equals r squared, it's a circle with center, origin, and radius r. So this one here is going through the points minus 3, 3, 3, minus 3. Sorry about the inaccurate drawing. So its equation is very simply x squared plus y squared equals the radius squared. So the radius here, the distance from the center at 0, 0 in all directions is 3. So this will be x squared plus y squared equals radius squared, or x squared plus y squared equals 9. So let's say I'm now asked to graph x squared plus y squared equals 36. That's really easy. It's going to be a circle because it's x squared plus y squared equals something. So you need to square root this. The radius is not 36, it's the square root of 36, or 6. So it's going to have center here. It's going to go 6 in all directions. So it's going to go 4, 5, 6 up to here. It's going to go down negative 3, negative 4, negative 5, negative 6 here. In all directions, it will go here to negative 6 and up here to 6. So all I do is join this in a circle, and I'm sorry that I am terrible at drawing circles, but it will look like this. They're so easy to graph. So we might get asked a question like this: where would this circle, I'm referring to the one in blue, intersect with the line y equals x? So you might remember from the first term, y equals x is the line that goes through the origin at 45 degrees. So this is the line y equals x. Now, unfortunately, we can't just look at the diagram and know what the point of intersections are. We know there's a point here and a point here, but we don't know what the coordinates are exactly. It turns out they're not going to be rational numbers. So how do we figure it out? Well, if y equals x, I can substitute that into this equation here. So basically, I'm finding the point along this blue circle where the x and y coordinates are the same. So substituting y equals x here, I'm just going to change the y's to x's. So I get x squared plus y I change to x. So I get x squared plus x squared equals 36. 2x squared equals 36 because x squared plus x squared is 2x squared. Divide each side by 2. and then square root. So when I square root 18, remember there's a positive and a negative solution. Over here, when I square rooted 36, I only took the positive solution because we were talking about the radius of a circle, which must be positive. But here, I'm just finding an x-coordinate. So when I square root 18, I have to take the positive and negative value. So what that means is x could be positive root 18 or negative root 18. This point here will be the point square root of 18 is the x-coordinate, but the y-coordinate's the same. So it'll also be root 18. And this point here will be negative root 18, negative root 18. All right? How easy is that? That's really all we need to know for circles. I'm now going to go on to the final topic of exponentials. So exponentials are the graphs of equations y equals a to the power of x. So just like circles and parabolas, these are non-linear graphs. Your graph will not be a straight line. So what I'm going to do is I'm going to label my axes, and then I'm going to graph these three equations, the red, the blue, and the yellow. So it turns out exponentials also have this characteristic shape. They either get large really quickly or small really quickly. So let's look at y equals 2 to the power of x. X equals negative 3, y equals 2 to the negative 3, which is 1/8. If x is minus 2, y is 1/4. We're just substituting each x value into the equation. So 2 to the power of 0 is 1, not 0, and then it's going to get big really, really quickly. So let's plot these points. So negative 3, 1/8 is very close to the axis. It's about there. So negative 2/4 is just a little bit higher, like there. And minus 1/2 is again just a little bit higher still, around there. Y-intercept is 1. In fact, it turns out if you have anything of the form y equals a to the x, or even y equals a to the minus x, that the y-intercept is 0, 1, because anything to the power of 0 is 1. We can't have that a equals 0, by the way. Okay, so then 1, 2 is here, 2, 4, 3, 8. You can see it's starting to get big really quickly. 4, 16 is all the way up here. So this is what an exponential looks like. Really close to the axis, and then it gets big really fast. So this is the graph of y equals 2 to the power of x. So if you change the value of a, it just makes it steeper. Y equals 3 to the power of x would also go through this point here. It would also have y-intercept of 1. It would be steeper, though. It would get quicker, faster. So what about 3 to the power of minus x? Well, here, if x is minus 3, y would be 3 to the power of positive 3, which is 27. Too big to fit on these axes. And then similarly, it will be 9, just substituting in all of these numbers. Once again, it will go through 0, 1. Now, if x is 1, y is 3 to the power of minus 1, which is positive 1/3, positive 1/9, and so on. So what will happen, it'll start at minus 327. I won't plot that because it won't fit here. So minus 2, 9 is up here at this point there. So it will go through minus 2, 9. It will go through minus 1, 3, 0, 1 again. And what will happen is it's going to get closer and closer, but never touch the x-axis. So 2, it's going to go through 1, 1/3, 2, 1/9 is about there. So you can see the opposite's happening. It gets really large over the left-hand side, but then it gets really small and closer to the axis. But it never actually hits the axis. So if you have one that's just in the form y equals a to the x or y equals a to the minus x, it will never, these ones will never hit the x-axis. So things are going to be a little bit different here because of this +1 in the yellow one. So again, we're going to take each value of x, substitute it into the equation. So I filled in the table of values, and let's go and see what the graph would look like. So 63 over 64, the y value of the first point here, so that's x and y, that's very close to 1. So it's going to be very close to minus 3, 1. So it's going to be like about here. The next point, the y value is still very close to 1. So minus 2, 15, 16 is about there. Minus 1, 3/4 about there. and it goes through 0, 0. So this one does hit the x-axis only because of this value here. So then 2, it goes through 1 minus 3, and then 2 minus 15, all the way down here somewhere. So it goes like this. So it still has the same sort of shape, and it still tapers off. What happens is this gets closer and closer to this line here, x equals 1, but never hits it. An exponential equation can be written in this form. This is a more general form than we used before. So it's plus or minus a number to the power of plus or minus x plus a number. It cannot, y can never be equal to this number here. Why? Because this can never equal 0, so y cannot equal, it's not allowed to equal 0 plus b. So an asymptote is like a no-go zone. So in this case, we can't have y equals 0 for the first two. So the asymptote was y equals 0 or the x-axis. They didn't hit it. But now because we've got the 1 here, we can't have y equaling 1 because this cannot equal 0. So what will happen is the exponential will get closer and closer to that asymptote as you go in one direction of x, and it will get either really large or really small in the other direction of x. So that's what happened in all the cases here. For y equals 2 to the power of x, it got closer and closer to the asymptote y equals 0 here, and then it got really large. If the power was negative, x was negative in the blue one, the opposite happened. It got really large, and then it got closer and closer to the asymptote. But it shouldn't ever actually hit the asymptote. So then what happened in the yellow one, because this 1 actually shifts it up, the asymptote is now y equals 1. So it got closer and closer to the asymptote, and then it got really, really small like this. Okay? So please ask if you have any questions. That's all we need to go through. Best of luck in the test. Though you're a superstar, you're going to absolutely ace it. Thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.